Okay, let's see the options we have for applying load on shell elements. So I will come here, use deform shape. So you see it's gone. Now I'm coming here again, deform shape. You can see it's showing dive right. I need to press here deform shape. It's coming to Z0. So I'm just showing typically one of the levels, then I will complete the loading later on. So let's select some of the shell elements just to show you how to select shell elements to ensure that you selecting right elements. If I come here to elevation YZ and coming to this elevation which is for grid F, so I'm in this, I can see here I'm in grid D, so I'm going to grid F. So if I select elements like these, you can see the walls wouldn't be selected. So if you want to choose wall elements, you always need to come to elevations and select wall elements. So I can easily select all elements here like that, and I'm sure that the selection elements are just floors. So if I come here and move back, I can see no wall element has been chosen. So the options we have for shell, if we see here in the small menu, I can assign mass, which is not a subject at the moment. I can assign uniform loads and temperature loads. If I come to assign an area loads, I have some other option. Gravity is the same as frame, uniform shell and uniform to frame, and surface pressure and temperature are the subjects we want to discuss in this course. So I'm coming to area load, uniform shell. You can see again the pattern of applying load is very similar to frame. So I can choose a type of load pattern here, is a global or local, and what load I have. For example, I can say okay Z, and here I can put -2 kilonewton per square meter or kPa, and I can say okay, replace it with the existing loads. So if I press apply here and I activate this and then press apply, you should be able to see the load, even the view title showing area uniform SDL. But why we are not able to see the load? If you pay attention, you see the elements are here is extrude. So this view is set on extrude option. If we come to general option, view type, change it to standard and apply, now you can see the loads. Okay, so it's showing 0, 0, -2. That means x, y, 0 and z -2. So if I change this one to gravity and change this one to 2 and select all of them again and apply, you can see the number is coming the same, because you choose gravity, but actually what you see here is x, y and z directions. That's how it's shown. So this is for area load. You have the same options here for add to existing load or delete existing load, and you can choose other options as we discussed before, so I'm not going through all of them. Also you can choose global and local. So if I come to local and choose 3 and then put 2 here and for example select them and apply, you can see the number is positive because 3 is upward in this case. If I activate local axis here for area and apply it, you can see 1 and 2, and based on right hand rules axis 3 is upward. That's why you can see here the positive number. So this is for area pressure. The other option we have is area temperature. So I'm going to another level. For example, I'm selecting those elements and then I'm coming to area temperature. Again, we have exactly the same options as frame. So I can choose thermal load expansion. Here give me the temperature gradient in 3.3. Why? Because the only when you use by element, automatically the expansion would be in both directions. This is you have considerable dimensions in these two sides. But if you choose 3 3, this is a minor dimension. For frame, you have one major actually direction, which is 1, because this is a rod element, and the two others are minor, 2 2 and 3 3. For shell element, 1 and 2 both are majors because of the shape of the element, and 3 is just a minor one, so you have it separately. So again, by element or by joint pattern, and I will explain joint pattern later. You need to define the joint pattern and assign joint pattern and then use it in loading. We will use all of them in soil pressure and water pressure. Okay, so those are the options we have. So I can again choose, for example, minus 30 degrees, and this is Celsius. So if you want to change it to Fahrenheit, you need to come here and choose a different option. You can see when I change it to Fahrenheit, the minus 30 changed to minus 54 automatically. Then you can apply. So this flexibility is available even during actually applying a load and when you are at the middle of the procedure. So this is a good flexibility. Or you can put here the number you want. For example, minus say 40 Fahrenheit. If I put something like that, you can see it automatically changed to Celsius. So you can do the same for any other loads that we discussed so far. You need to put the unit in front, and you can see it's automatically converted to the defined load units here. So say minus 30 and just apply, and you can see all four corners are shown minus 30. If you have a joint pattern, they could be different. The other option we have is uniform to frame. So this is good when you have a one-way slab and you want to apply load. For example, here we have a kind of composite slab and I want to apply load on these beams. If I simply choose for shell, if I choose applying load, it coming as a two-way. So the load wouldn't be transferred directly to the beams, 50% here and 50% here of this span. It's coming a triangle for this, a small triangle for this, and we have two trapezoidal load actually area for these two. So if you make it like a membrane, you don't worry about that because it's automatically will be transferred mainly to the beams, but still you have that small areas. So what you can do, the easiest way is coming and selecting this shell element, and then if you want to apply load, you can come assign area load uniform to frame, and then here you say, okay, for example, this is a live load, global gravity, and you can choose here is that one way or two way. So if you choose one way and then say, okay, I have a live load of say 4 kPa one way, and then apply it here, the way it will be distributed is just coming to the beam, so the load wouldn't be transferred to these two, and that one way or two way will be recognized by SAP based on the ratio of the width to the length of each span. Now let's show you how to use joint pattern and how to apply surface pressure. So let me come to this view. I want to apply soil pressure on those retaining walls. So the first step, just to make it more clear, I'm coming here and I select by property area section for wall, which is 200 wall, and select it, and then come here, show selection only, close, and I remove this one just to make it more clear. Then I'm zooming here just to give you a better sense. I will replicate few of those elements one level up. So I press Ctrl R, I'm coming here, DZ3, because this is 3 meters high. I need 1, and I don't want to delete the original, so I apply. So I have 1 level more. To have the more accurate joint pattern, it's better to divide shell at height, because based on the number of joints you have along the height, the formula will work and give you the numbers, and then you can define your load patterns for pressure. So what I want to do, I want to, just to give you a little bit sense, I will subdivide this one to 3 at height and this one to 6 at height. So I'm selecting those. I'm coming here in area local axis to see what areas I have. You can see the axis 1 is here, so this is 1, 2 and 3. This is 1, 2 and 3. There is again a small bug here in SAP. If you remember, guys, we reverse this axis tree manually ourselves, and this is naturally created as it is. So sometimes SAP gives you the wrong result, but I will raise this one with CSI. Here you can see mentioned that we want to divide element along edge from point 1 to 2. I put 1. Along edge from point 1 to 3, I put 3. But because I reverse this local axis, if I apply, you can see it's showing like this, which is not correct. I press Ctrl Z, and then I'm doing exactly the same without touching anything here, and I apply. And you see it gives me the right division that I want. So what I can do here, just simply reverse the command you have here, and we will discuss this one with CSI to fix it. So this is what you need to do. This arrangement is not right based on this command and this local axis, but that's fine. Let's just move on. We need to be agile and flexible always. We just need to find the right and proper solution. So I will divide this one to 6. Okay, so I have this arrangement now. What I need to do, I need to define joint patterns. So first I need to come here, joint patterns, and I just need to define the name of the patterns I want to use. Just to make this practice more sensible, I assume that this is like a water tank. I have water pressure one side and I have soil pressure the other side. So I will define 2 joint patterns here. Soil, I can rename this one, so I can say change pattern name, so this will be soil, and then water, and I can add new pattern name. Then I need to come to assign and assign my joint patterns. So what we need to do here is we need to put this formula and create the pattern. I have 2 methods of creating this joint pattern. One is X and Y and Z multiplier plus D, which is a very global option. The other one is the Z coordinate at 0 pressure and weight per unit volume. I will explain both of them. So let's start from the global one. What I want to see here is, say we have a soil pressure at one side and water pressure the other side. So water is 10 kilonewton per cubic meter. There is no other factor. The lateral factor is 1. But soil, we assume that, for example, we have a sand, so the phi something around 30 degrees. So the Ka factor, which is active soil pressure, is something around 0.3 times 20 kilonewton per cubic meter weight of soil. We have 0.3 times 20 times the height. And the other option I want to consider is I have, for example, 10 kPa surcharge load here. That should be multiplied by 0.3. I have a 3 kPa surface pressure, but it's a fixed number. It's not changing at height. When we talk about surface pressure, what you need to consider is the pressure is always towards the surface. So when I put any number here, if the number is positive, that means pressure is towards this surface. It's like a gravity. You don't need to put negative number. So don't be confused about axis 3 is toward the surface. If I say top pressure, this pressure is this way. If I say bottom pressure, the pressure is that way. So axis 3 is just defining top and bottom surface. Top is the positive direction of axis 3 and bottom is the other side, which is the negative direction of axis 3. So I need to have positive numbers here. Positive numbers start from 0 going down. So I will consider using one factor here, and I will apply the surface pressure multiplying by this pattern later on. So I can just show you how it works. In this formula, when we say CZ, Z is exactly back to this orientation. So from here, Z is positive. From here down, Z is negative. So if I just simply put 1 here and select all those joints around the shells, all of them shall be selected like this. So we shouldn't miss anything. All of them are selected. If I press apply here, you can see this is Z0. From Z0 below, depends on the Z coordination, you can see -1, 2, 3, and when we're coming up from 0 to 3. Because we have more joints here, so it automatically pick up all joints and give you the number, depends on the Z coordination. Is that useful? No. Currently we have pressure here like a reverse triangle, and we have another pressure here like this triangle. How we can make it work? What's the pattern we are after? We are after 0 to +6 here, because the pressure is in this way. So if I change this constant to -1, it is almost helpful. I can say preview selection, and if I press apply, you can see it's coming from -3 to +3. Still, it doesn't give me what I want. I need 0 to 6. So what I can do, I can put a constant 3 here, and then again preview selection, and when I apply, now I have from 0 to 6. That's exactly what I want. So I need to know how this pattern works. There are some other options here. Another option is 0 negative values and 0 positive values. This is for all values. Currently, this is what I used. So I will delete this pattern just to show you the rest. Preview selection and apply. Now I'm coming and choose 0 negative values. And I'm coming to add value, and I'm just putting here 1 just to show you what's going on. So 0 negative values. If I select all and apply, you can see it doesn't give me the negative values. All of them are 0. So 0 for all negative values. This is exactly what's happening here. If I choose this preview selection and put 0 for all positive values and apply, you can see below, but you don't see anything above. That means when the Z is positive, all values would be 0 for positive Z's, and when we chose this one, that means wherever Z is negative, the values would be 0. So you need to see how it works for you. But let's back to our original panel. So the target we have is 0 pressure here, and this pressure increasing based on the height, so going to 6. So I'm coming here, all values, I'm replacing this one, put -1 and 3. So here what we have is -1 times 3 is -3 plus 3 is 0, and the end is -1 times -3 is 3 plus 3 is 6. So if I put preview selection here and then apply, I can see the pattern I want. So this is the pattern I have for soil. What I need for water, I explain you the pressure is towards the surface. So when the axis 3 is here, when this number is positive and I choose top surface later on, the pressure is towards top surface. But if I choose bottom surface, the pressure is towards bottom surface. So I can say I can use the same pattern for water, just the constant number that will be multiplied to them is different. Sometimes you may want to apply in a different pattern and consider some other factors you have, like for example Ka, and just add a specific gravity of the soil. So that can make them different. But if I come to water, literally what I need is very similar to this. So I'll keep this one and I put preview selection and apply. So this is one pattern. The other option I have is Z coordinate at zero pressure. So how this one works, say let's change water for this one, just for practice. So I'm coming here, I have a table here, and I can add to this table by adding more numbers. It could be as many as I want. And I have a uniform value per unit area here. How it works, it gives me what coordinate I want to have zero pressure and what's the unit weight I want to have it here. So if I come here and mention, okay, zero coordination for me is here. I'm just want to show you what's happening here, and then the number I have for water is 10. Yes, and here I will put all values for water and I will replace it. So I choose preview selection and then I apply. What you see here is the unit weight is here, but again because of the numbers we have, it's showing like this. So I put Z coordination 0 and I put 10 for gravity. So when Z is going down, the gravity apply this pressure, but when we're coming up, actually we're losing gravity, so the number is negative. How I can make it right for myself, I have two options. Either I can put a number here which is 30, so that 30 will be added to this value like what we have here, like CZ plus D. So this is specifically just CZ plus D. The only difference is that you can put this unit weight here. So if I come here and replace it and say preview selection and apply, it gives me what I want. The other way, which is more logical, is you will define where is the Z coordinate for you for having zero pressure. So for us, zero pressure is at 3 meters height. So I can put 3 meters height here, and I don't need to put anything here. I have 10, and then I put preview selection and I apply. It gives me exactly the same number. You saw it didn't change. So I have from 0 to 60 joint pattern values for water pressure. So let's see how we can apply surface pressure based on this joint pattern. So I'm coming here, use preview selection, I'm coming to assign area loads, I'm coming to surface pressure all. So here what I have water. Okay, so let's start from water. Water needs to be applied to the bottom surface. So I'll keep this one bottom surface, and then pressure could be by element. This is a constant pressure. I'm not using this one for water. By joint pattern, I'm choosing water. Multiplier, I don't need to add 10. I just put 1 because already I applied the unit weight in my joint pattern. Shall it be positive or negative? It shall be positive. It automatically understand that this is a pressure to the bottom surface. So when I apply, you can see the arrows this way. So if I zoom in, you see the numbers are from 0 to 60 kPa. This is for 6 meters water, which is correct. Now I need to apply soil pressure. So I'm changing my load pattern to soil. I want to apply to top surface. The joint pattern would be soil. So my soil joint pattern was from 0 to 6. What I have as a surface pressure is K active of soil, which is 0.3 in this case, and 20 kilonewton per cubic meter specific weight of soil. So the result would be 6 kilonewton per square meter per meter height. So that would be from 0 to 6 times 6, which is 36. So the factor I have actually is 0.3 times 20. So I need to put here 6. And the rest are okay. I put Pervious select and then apply. So you can see it's from 0 to 36, which is correct. What else I have? I have a constant surface pressure of the surcharge load, which is 0.3 times 10 is just 3 kPa. How can I apply? I need to come here, add to existing, by element, and this number pressure would be 3, and then I can choose previous selection and apply. You see the numbers actually increase and 3 kPa added to them from 3 to 39. So this is how we use this joint pattern and apply soil pressure or water pressure, or you can do the same for thermal loads. You can use the same based on the gradient of the heat. You can define the joint pattern and you can apply a different thermal load along the element. So this is what I wanted to share about applying loads on elements and defining load patterns, load cases, and load combinations. Hope you guys got some clarity about this part of modeling. I will complete my model, apply some reasonable loads, and complete my load combinations for the next session. And next module we will start tweaking the model a little bit, see how we can ensure that the errors are minimum, and then we will run the model and do the analysis, and I will show you how you can check the internal forces and displacement, and also how you can do some troubleshooting and update your earthquake load based on modal analysis results.